So, today's lecture we are going to resume our discussion of multivariable calculus. So, last time I had introduced or rather recalled the definition of derivative in higher dimensions, and so let's start with the example that I had started towards the end of last lecture. So, let Mn R be the set of n cross n matrices and let Snr be the set of n cross n symmetric matrices. Note that MnR and Snr are vector spaces with the usual operation of matrix addition and scalar multiplication, and Snr would be then a subspace of Mnr. We want to regard these as Euclidean spaces. So, when I say regard these as Euclidean spaces, what I mean exactly is I want to give an isomorphism, linear isomorphism from Mnr to Rn squared, that is one, and the other one is from the space of symmetric matrices to R n into n plus 1 by 2. And the isomorphisms are as follows. So, for Mnr I just take, so I define this map phi of A matrix A, here A is an element of Mnr, so it is a matrix. What I do is I just put out the entries of A row by row. So, this is the first row, this is the second row, and so on. So, altogether I will get n squared entries. So, I get an element of Rn squared. And it is easy to check that this map is linear and 1 to 1 and on to. And as for the space of symmetric matrices, I do something similar. I just well, the first thing, first row, I just put out the first row of A. As for the next, I do not start with the full second row, I start with A22, go all the way up to A2n. And for the third one, I would start with A33, go up to A3n, and so on. So, the final entry will be ANN. Again, just to verify that we have a map into this Euclidean space, notice that there are n elements here in the first block, then n minus 1, and so on all the way up to 1. So, the number of coordinates here would be n plus n minus 1 plus n minus 2 and so on plus 1, which is indeed n into n plus 1 by 2. And again, this map C is also a linear isomorphism from this vector space to that. So, once I have this isomorphism, I can just basically, so with all the notions that we have defined here, there the domain was an open subset of some Euclidean space. So, because of these isomorphisms, I regard these as identified with these Euclidean spaces. So, I can still talk about differentiability of functions defined on these spaces Mnr and Snr. So, I am going to give two examples. The first one is f of x equals x squared. Here of course x is an element of Mnr, so which is a n by n matrix. So, and here x squared is usual matrix multiplication. So, the claim is that we claim that f is differentiable at all points of Mnr and its derivative at a point at A in Mnr is the linear map dfa, remember that if we had a map from an open subset of Rn to Rm, the derivative was a linear map from Rn to Rm as well. So dfa here would be a map from MNR to MNR, and the claim is that this linear map is given by its action on a element H is HA plus AH. For all H in MNR. Now here I just wrote down the formula for the derivative, and let's verify that this is indeed the derivative going to the definition. In the next step I will show how to get this in the first place. So but to verify that this is the derivative, we just have to check that this is the derivative of f at A. Consider, we go back to the definition. So I have to look at f of A plus H minus f of A minus dfa of H, norm of that divided by norm of H, limit H going to 0. Now remember that MNR has been identified with Rn squared. So when I say norm of something, norm of a matrix, we have to regard MNR as an element of Rn squared and take the norm in the usual way. So let's see. So here this is, if I do the calculation, I get limit H going to 0. F of A plus H is A plus H squared minus A squared minus, here this is by definition H, well, from the formula that I wrote down here, HA plus AH divided by norm H. And if we expand out A plus H squared and so on, so finally I will be left with various terms cancel out. I will be just left with limit norm H squared divided by norm H. As I said, the norm here on the space of matrices comes from Euclidean space. So to proceed further, let's see what the norm of a matrix is actually. Here, if X belongs to MNR, norm X is, so I defined that isomorphism from MNR to Rn squared, so I will use that isomorphism. So this is the definition of norm X. Norm X is norm of phi of X. The point being that this phi of X is an element of Rn squared, and this norm is the usual Euclidean norm. And so, and remember, phi of X was just the entries of X laid out row by row. So if one takes the Euclidean norm of this, one gets square root of sigma xij squared, ij equal to 1 to n. So all we are doing is we are just saying that this norm is just amounts to saying that you square all the entries of X, add them up, and then take the square root of the sum. So with this definition of norm, notice that now I want to go back to this norm of h squared. First, notice that if I look at the matrix h squared and take the ijth entry, this is the same thing as hik hkj k equals 1 to n. This is from the usual definition of matrix multiplication. So this is these are the entries of h squared, the matrix h squared. Now when I take norm, I have to square each entry and add them all up and then take the square root. So but before I do that, let me see how big can this be. So this is by this Cauchy-Schwarz inequality, this is less than or equal to summation square root hik squared k equals 1 to n square root k equals 1 to n h k j squared. Well, each one of these will be less than or equal to norm h times norm h multiplied equal to norm h squared. So the point is that every entry of the h squared matrix is less than or equal to norm h squared. So let's use that. Therefore, if I look at the norm of this h squared matrix, that's equal to, by definition, I look at its entries and sum over I and j. Now each entry, I have to square this and then sum them up. So now each entry is less than or equal to h squared, but I'm squaring them, so I'll get h to the 4 here. So this is less than or equal to square root, and there are n squared terms. So n squared times norm h to the 4. So this is equal to n times norm h squared. And that's good enough for us. So I get this estimate. Therefore, now I will go back to the limit this divided by this, h going to 0 is less than or equal to, because of this what I just proved, limit h going to 0. So I get n h squared divided by h is equal to limit h going to 0 n times norm h, which is 0. So the upshot is that I started with this. I wanted to claim that dfah satisfies the condition that this limit should be 0. So and we checked that it does. But this process does not, this was just a verification of an expected, we already guessed, had a guess for the derivative and then we verified. But suppose we want to find the formula for the derivative, then I go back to this directional derivative interpretation. Suppose, but that involves an assumption. If we knew that, which is satisfied in this case, if we knew that all partial derivatives f exist and are continuous, then we know that dfa acting on H is nothing but the directional derivative of f along the direction H at the point A, which I had denoted by H of f, and which was in fact, this is by definition, H of f is d by dt f of A plus t times H evaluated at t equals 0. This was the definition of directional derivative, and last time I had remarked that the directional derivative is related to the full derivative, the Frechet derivative, by this formula. Well, they are literally equal when the full derivative is evaluated along that specific direction. This is under the assumption that if you know that all partial derivatives of f exist and are continuous. So now let me just say that this hypothesis, all partial derivatives f exist and are continuous, is satisfied in our case simply because all the component functions, note that the hypothesis is satisfied since all the components of f are, well, the function f of x was just x squared, where x is a matrix, and f of x, all the components of f are actually just polynomials in the input variable, polynomials in the input variables. Therefore, the all partial derivatives exist and they are polynomials as well. But that is all we need to say at this for this hypothesis to be true. But if we actually want to know what the derivative is, we use this formula. So we already know that dfah is ah plus ha according to the previous calculation that I did, but now let us use the right hand side. Now f of a plus th is by definition a plus th squared, which is a squared plus tah plus tha plus t squared h squared. Yeah, right. So this is this. Therefore, df of a plus th by dt at t equals 0, I just have to differentiate with respect to t in the usual sense here, and then basically I will get 2t here in the last term, and this first term disappears because there is no dependence on t, and in the second two terms the t becomes 1 after differentiating. So I will just, so when I put t equals 0, finally I will get h plus ha, which is the formula that we had earlier. But the point here is that we are able to derive the formula if we use this directional derivative interpretation of the derivative acting on as a linear map. So that is one of the main uses of this. It actually helps us to compute derivatives. because essentially, as you can see here, the problem gets reduced to a problem of one variable calculus. There is only one variable here. Since I have restricted f to the straight line a plus th, well, the only variable here is t. So I can do the calculation quite easily. Now the second example is something similar. So this time I will take f from MNR to SNR, symmetric matrices, and again the input is x and the output is, instead of x squared, I will take x times x transpose. The point is that whatever x is, x times x transpose is always going to be symmetric. So I actually get an element of SNR, not just any other matrix. And again, one can do the calculation, directional derivative interpretation here as well, because the hypothesis is again satisfied. All partial derivatives of f exist and are continuous, because again the components of f are just polynomials in the input variables xij. So we can use them, and this time we find that dfa h, now it turns out to be a times h transpose, a times h transpose plus h times a transpose. This formula I will use later on in the course. So this is the final. So I have been saying that one has to be a bit careful when dealing with these different concepts of derivatives. So let me just make a remark. The existence of all directional derivatives at a point, here all refers to all possible directions. So existence of all directional derivatives at a point does not guarantee that the function is differentiable at that point. So the standard example is, here's an example, f from, I'll define a function from R2 to R by f of xy is x squared y, x to the power 4 plus y squared if xy is not equal to 0 comma 0, and f of 0 comma 0 I just define it to be 0. One can check that at the point 0 comma 0 all directional derivatives of f exist, but f is not differentiable. One can check that all directional derivatives exist at 0 comma 0, and the way one checks is the one just goes definition of a directional derivative. So once you start with, let v equals v1 comma v2 in R2, then v of f is d by dt f of, now the point is 0 comma 0. So, the straight line was p plus tv. P is the origin. So, all that I get is p of tv at t equals 0, and this would be the derivative. F of tv would be well, tv1 tv2. So, here I will get t cubed v1 squared v2, and here I will get t to the 4 the v1 to the power 4 plus t squared v2 squared, right, evaluated at t equals 0. Of course, this t squared cancels out and I am left with d by dt. So, I will get t v1 squared v2 t squared v1 to the 4 plus v2 squared at t equals 0. And the point is that this function, so two cases will arise if v2 is 0 or v2 when v2 is 0 and v2. If v2 is 0, we get v of f. If v2 is 0, well, independent of what v1 is, the numerator itself becomes 0. So, the directional derivative would be 0. If v2 is not equal to 0, one can check that what the specific value does not matter, then the denominator does not vanish when t is 0. So, we know that by elementary calculus that this derivative does exist. If v2 is not 0, we know that the one variable derivative exists at t equals 0, simply because the denominator does not vanish at t equals 0. Now, why is f not differentiable at f is not differentiable in the Frechet sense at 0 0 because of the following. So, just like in the one variable case, we have let f from to Rm, U is an open set in Rn if f is differentiable at p in U, then f is continuous at, so differentiable in the Frechet sense will guarantee continuity at that point. And one can check that this function, what I have here, is not continuous at the origin. So, that is the reason why it is not differentiable. So, in particular, the existence of directional derivatives will not imply, right. So, in the next class, I will talk about one of the main theorems in multivariable calculus, namely the inverse function theorem. So, we will stop here.